Hi, my name is Sydney Grushaw, and this is my Chapter 16 review video. And Chapter 16 was really about electricity and protons, neutrons, electrons of an atom, and a lot of ways of charging. To get started in this review video, the first section is about electricity. And there's 3 principles of electric charge right here, here, and here. The first one is that there's 2 types of charges. There's protons and neutrons, and these are both symbolized by the letter Q. The protons are positive, which is why it's positive Q, and the neutrons are negative, which is why it's symbolized as a negative Q. An important rule to remember when focusing on electricity is that like or similar charges repel from each other and opposite charges attract. The second rule or principle of the electric charges is that electric charges are conserved. And then the final one is that there are 2 types of materials when it comes to electricity. There's conductors, which are usually metals, and they have negative charges, and these electrons move freely within the conductors and are found anywhere within them. And then the second type of material is an insulator, which the electrons are locked into place and stay in one spot. The next part about electricity is that there's actually such thing as a neutral charge, which is where an object has just as many protons as it does electrons, so that the net charge is 0, which means it has charges, but there are enough protons and electrons to make everything equal. Another important thing to remember is that when charges move around, only the electrons move, the protons stay in place. There are a few methods of charging, one which is contact, or known as friction, and this is when you bring 2 objects together. An example of this is bringing a metal rod or plastic rod with fur. And then a second method of charging is by induction, and an example of this is the Van de Graaff machine with a metal pie tin. The next part of the season is ways of charging, and what we're looking at right now is a carbon atom, and in this carbon atom there are protons, neutrons, and electrons, and we notice that in the center of this atom there are 6 protons and 6 neutrons, and then around the rings, or better known as the electron field, there are 6 electrons to count. Now, from what we just learned, this carbon atom is a neutral atom because it has just as many protons as it does electrons, so that the net charge equals 0. So when you're charging by conduction, you need a conductive sphere, and the way we use this is by using a Van de Graaff, which is basically just a large circle, and the machine moves around on the inside to generate electrons. And then if we take a negative rod and touch it to the Van de Graaff sphere, it turns neutral. And once we have touched it, both of the objects end up with the same net charge after they touch. Now, a really important part of the season is Coulomb's law. This is signified by an electric force pulling up, and gravity as well are actually equal. Now, 1 coulomb is equal to 6.25 times 10 to the 18th electron, and the charge of an electron is negative 1.6 times 10 to the negative 19th power, and the charge of a proton is actually the positive of that. It's 1.6 times 10 to the 19th. The electron is negative because it contains a negative charge, and the proton is positive because it has a positive charge. Now, if we look at the law itself, it's symbolized down here. F electric equals Kc times Q1, Q2 over R squared. And what each of these means, the F electric is the electric force between the 2 charged particles. The Kc symbolizes Coulomb constant, which is a number that we represent as 9 times 10 to the 9th power. The Q1 is the amount of charge measured in coulombs, and the Q2 is the other amount of charge measured in coulombs. And this is all over the distance of r squared, which is the distance between charges, and it's the distance from the midpoint of each charge. A way to remember this is by the saying, ferret equals knits queen's quilt, right? So this next part of the video, we're actually going to practice Coulomb's law. So right here, I have a problem, and it says two electrostatic point charges at plus 60 mu coulombs and plus 50 mu coulombs exert a repulsive force on each other at 175 newtons. What is the distance between the two charges? So what we can do here is write out Coulomb's law. And since we're trying to solve for distance, which is r, we want to get r alone, so we can actually rewrite the equation to be r equals the square root of Coulomb's constant times Q1 times Q2 all over Fe, or the force electric. Now let's make a table of our knowns. We know that our force electric is 175 newtons. Our Q1, which is our first amount of charge measured in coulombs, is 60 times 10 to the negative 6 power coulombs. Our Q2, which is the other amount, is 50 times 10 to the negative 6 coulomb. And then our final known is Coulomb's constant, which is 9 times 10 to the 9th newton meter squared over coulomb squared. Now let's plug in our information into our new equation right here. So we have r equals the square root of 9 times 10 to the 9th multiplied by 60 times 10 to the negative 6 power times 50 times 10 to the negative 6 power, all divided by 175 newtons. Now plug that into your calculator and see what you get. And hopefully when you plugged that in, you should have gotten that r equals 0.393 meters. If you did, good job. The next part of the season is electric fields, and in these there are test charges, which are regions where electric forces or charges can be detected. There are as well field forces, which act at a distance. They're not contact forces, and they can be visualized with field lines. And electric field lines point in directions. The positive test charges could be moved, and the test charges are always positive. Oftentimes there are fields with multiple charges, and between two like charges it is possible to have a field strength equal to 0 between them, and two opposite charges, if one is negative, as shown in this example, and one is positive, the negative pushes and the positive pulls. The next part of this season is electric field math. The common gravitational field strength is equal to 9.8 newtons over kilograms. Electric field math is symbolized by vectors. And the formula for the electric field is E equals kc q over r squared. And the force for charge, the units are newtons over coulombs. And what this formula actually stands for is electric field strength is equal to Coulomb constant which is multiplied by the charge producing the field all over the distance squared. And an example of this would be 1 coulomb over 9.8 newtons. And if we think about it, we can switch that to 2 coulombs over 19.6 newtons. The next part of the season is the Faraday cage, which comes in all shapes and sizes, but all of them use a metal screen that conducts electricity, creating a shielding effect. Faraday cages shield their contents from static electric fields, as electric field is a force field surrounding a charged particle such as an electron or proton. A Faraday cage distributes the charge or radiation around the cage's exterior. It cancels out electric charges or radiation within the cage's interior. Basically, a Faraday cage is a hollow conductor in which the charge remains on the external surface of the cage. As stated before, a Faraday cage is a conductor. This is because the exterior is a metal cage which charges only its surface and has no effect on its interior. Certain examples of Faraday cages are esoteric lab settings, cars, buildings, and microwaves.